How do you design compensators for system stability? Imagine trying to keep a spinning top balanced on your finger. If it wobbles too much or spins out of control, you need to adjust how it moves. That's what designing compensators does for electrical control systems. It's all about shaping how the system responds to keep it stable and performing well. First, you start by analyzing the system's current stability. Engineers use tools like Bode plots, which show how the system reacts at different frequencies, or Nyquist plots, which help visualize stability margins. Root locus plots are also common, showing how the system's poles move as you change gain. These tools reveal gain margin, phase margin, and where the poles and zeros are located. These are key indicators of whether the system is stable or not. Once you understand the current stability, you decide what needs improvement. If the system tends to oscillate or overshoot, you might want to increase the phase margin. If it struggles with steady-state errors, you focus on steady-state accuracy. To do this, you choose the right type of compensator. Lead compensators add phase lead, which means they give the system a boost in phase at certain frequencies. This helps improve transient response and increases phase margin. They usually have a zero placed at a lower frequency than their pole, which creates the positive phase shift needed. Lag compensators are used when steady-state accuracy is more important. They increase low-frequency gain but add phase lag, which can reduce phase margin. They are good for systems where steady-state error reduction is a priority. Sometimes, you combine both types into lead lag compensators. These give you the benefits of faster transient response and improved steady-state accuracy at the same time. Designing a compensator involves several steps. First, you identify the system's performance needs, like how fast it should respond or how much overshoot is acceptable. Then, you analyze the system without any compensation to see where it currently stands. Next, you pick the type of compensator based on what needs fixing. After that, you calculate the parameters, such as where to place the zeros and poles, to shape the frequency response. This involves tuning the compensator so it adds the right amount of phase lead or lag at the critical frequencies. Once you have your initial design, you verify it by plotting the system's response with the compensator in place. You look at the new stability margins and transient behavior. If needed, you go back and fine-tune the zero and pole locations. This iterative process helps you reach the desired stability and performance goals. In practical electrical engineering, compensators are often built using resistor-capacitor networks. For example, a Type 2 compensator uses resistors and capacitors to create zeros and poles that shape the loop gain and phase. Adjusting the resistor value can change the bandwidth and gain, affecting how quickly the system responds to load changes. Changing the capacitor influences the gain at specific frequencies, helping control transient settling time. By carefully selecting resistor and capacitor values, engineers can tune the compensator to keep the system stable and responsive. This is especially important in power supplies, motor control, and other electrical systems where stability under different conditions is vital. In summary, designing compensators for system stability involves analyzing the current system, choosing the right type of compensator, and tuning its parameters to improve phase and gain margins. Using RC networks to implement these compensators allows precise control over the system's response, ensuring it remains stable and performs reliably during operation.